I'm talking about, well, let's stick with our water waves for a minute. Okay, so I'm standing on the beach, the water waves are coming in. Again, if it's long, it comes in slow, right? 1 wave per second if it was 10 feet long. But if it's only 1 foot long, we'd have 10 waves coming in per second, right? Because of the difference in length of our waves. Which one is going to carry the most energy?
The shorter waves.
The shorter one, because they're coming in faster, right? If you're standing on the beach and you have a wave just coming in nice and slow, right? You can stand there, it can hit your feet, all that kind of thing, doesn't knock you over. If a storm's coming in, so those wavelengths are short and they're coming in really fast, they can have a lot of energy behind them, and it can knock you down, okay? Light waves. Your longer wavelengths are going to be things like radio waves. Then we get up to microwaves, and eventually infrared. Okay? Radio waves can be fairly long. They can be 1 meter or more long. Okay? When you start getting into infrared, they're getting much shorter. And then you get into the visible light range. Okay? Now, visible light range is about 750 nanometers going to 400 nanometers. So we're getting pretty short when we're talking about visible light. All right? And this is where you get the rainbow, right? The red, orange, yellow, green, blue, etc., going to violet, right? That's your visible light spectrum. Okay, between about 750 nanometers to 400 nanometers. When you are shorter than that, that's when you start getting into ultraviolet or X-rays or even gamma rays, right? Or even shorter, okay? Which one has the most energy? Up here, the gamma ray, right? The long ones, just like we said with the water waves, the long ones are going to have very little energy. We usually don't get that worried about having a radio bias, okay? Even though there's radio waves going through the air and everything else. We do start getting worried about having X-rays and gamma rays beside us, right? And ultraviolet even, right? Because that can still cause skin damage and things like that, okay? Because they're high enough energy, they start having damage. Now, first of all, let's just relate the wavelength to, we've said that they're inversely proportional. Let's look at an actual equation of how it looks. When you're talking about light waves, then, and this equation is on page 214, you have lambda V is equal to C, okay? Now again, let's think about this in terms of a water wave for a second. Lambda is our wavelength, so you're taking wavelength times the frequency, okay? So if wavelength is in something meters and frequency is in per seconds, right, hertz, 1/2, then your speed is going to be something in meters per second, right? And I could calculate that for a water wave. I could figure out how many seconds it takes. For the one that we said was, well, we said feet. 10 feet would be what, about 3 meters? Just rounding off, that's not right, but still. 3 meters in 1 second, right? Would be our speed, okay? When we're talking about light, because we're not talking about these bigger waves and things like that, what we're talking about instead is the speed of light. And that is a constant. So if we know the wavelength, because the speed of light is a constant, we can calculate the frequency, okay? And the speed of light is one of those constants I said is in the back of your book. Depending on how many significant figures you wanted to keep, we could use, for right now, we'll use 3.0 times 10 to the 8 meters per second. It gives a lot more significant figures in the back of your book. It's like 2.99 something or other, right? Okay, but we'll use that for right now. That C is a constant, it is the speed of light in a vacuum. Yes?
So instead of putting C, why don't you just put 3.0 times 10 to the 8?
Because most of your equations will put it as C. We're going to use several equations that just put it in as a constant C. Most mathematical equations are like that. We're going to have several constants. That rather than constantly putting the numbers into the equation, they usually write it with a symbol, and then when you do the calculation, you have to put the number back in, right? Does that make sense? It's like pi. We normally don't write the number pi. We just write the symbol, and then when we do the calculation, we put the number back in.
So could we use that to calculate like the speed of a gamma ray or something? Because we have the values listed, so if they give us like the wavelength of something and maybe its frequency, we can calculate how fast it's going?
Well,
Or are these
because
only-
gamma rays is electromagnetic radiation. That's light, right? It's just not visible light. It's still going to have the same speed, okay, at least in a vacuum. And we're not going to deal with going through substances and stuff. We're going to deal with the speed of light in a vacuum. But what we can do is we can say, I know the wavelength of light for the wavelength of a gamma ray, and therefore I can calculate its frequency. Or the other way around, I know its frequency, I can calculate its wavelength, okay? But it is still electromagnetic radiation. All electromagnetic radiation will have the same speed. That would even include things like microwaves or radio waves or whatever, because they're still electromagnetic radiation, okay? All right, so let's do a calculation. This is over on page 216, practice exercise 2, okay? And it says a laser used in orthopedic spine surgery produces a radiation with a wavelength of 2.10, and that italicized U, got it? That italicized U, that's why we take out some of the pages, is it's so big when you have all of them, but then you have those constants in the back that you need anyway, so. Okay, 2.10 micrometers. What does micro mean? That italicized U, what does that mean? 10 to the negative 6th, right? Okay. Calculate the frequency of this radiation. Okay, and then we're gonna go on to calculate just a little bit differently with the B part. Okay, so frequency is going to be equal to, remember originally it was frequency times lambda equals C, right? So now it's going to be C over lambda. We have lambda and we have C. Okay, and our lambda was 2.10 micrometers. So in order to get this to work, we're going to have to convert micrometers. Now, we said this several chapters ago, but I'm going to go through it again. There's two ways I can write this. If you're using the table that we had that said what a micrometer was, it will tell you that it's 10 to the negative 6th. That means that has to go in front of the meters part. 10 to the negative 6 meters for 1 micrometer. That's how you read that table. If you prefer positive exponents, it is the same thing as saying 1 meter is 10 to the positive 6 micrometers. It doesn't matter which one you prefer to use. Just realize if you're looking it up on that table because you wrote it on your 3x5 card from the table because you don't remember what micro is, then it's 10 to the negative 6th. Is this making sense? Are we good? Okay, so whichever one we choose to plug in, let's do 1 micrometer is 10 to the negative 6 meters. And plug it in to solve for frequency. Okay, again, the unit of frequency will be 1/2 second, which is called a hertz.